The parts holding modern engines and machines together take millions of load cycles before you finish lunch. That is why forging exists. Not just to shape steel, but to rearrange the grain inside it so the finished part outlives decades of stress that cast metal cannot handle. Presses of 17,000 tons work at the extreme edge of that idea. Watch a 37-foot crankshaft that costs more than a house. "17,000 tons of squeezing force pressed into one machine. That is the kind of number that changes how you think about a piece of steel. A press this size does not exist because engineers wanted a big toy. Nobody signs off on a building this expensive for fun. It exists because certain parts of the modern world cannot be cut, cast, or welded into shape. They have to be forged, and forged from very deep inside. The bigger the press, the thicker the workpiece it can reach through. You are looking at a machine that can push force all the way to the core of a steel cylinder the size of a small car, and rearrange the metal grain in there so the finished part will still be alive after decades of load. Everything you see later in this video, wheels, shafts, rings, crankshafts, begins with a press like this one. Then things get hotter. The billet comes out of the furnace glowing the color of a sunset, and the crew treats it about as gently as one. Steel is difficult to shape when it is cold. Heat it into the right range, and the same steel behaves like very stiff clay, still solid, but willing to move if you push hard enough. That is the whole trick behind forging. The press does not smash the workpiece in a single blow. It squeezes, releases, rotates, squeezes again, working the metal in patient cycles. Between hits, the workpiece is turned by a manipulator because a lopsided squeeze gives you a lopsided part. Steam and sparks come off with every stroke. The crew in white suits stands well back, and you understand why. What matters is not the drama on the surface, but the invisible change happening inside. The crystal grains are being flattened, aligned, and packed tighter. A 13,000-ton hydraulic press does not slam the billet, it leans on it, and it leans hard. 4 columns take the reaction load. The daylight, the vertical space between the tools, opens 8 meters, enough for parts as tall as a 2-story house. Water hydraulics move the ram down the 4.5-meter stroke. The steel does not really have a say in the matter. Before a press this big can flatten anything, somebody has to flatten a large section of the factory floor. The frame arrives in pieces because no truck on Earth is long enough to carry it whole. Cranes lift ring bases, columns, and crossbeams into a pit engineered to survive the reaction load. Watching it come together looks less like assembly and more like construction of a small stadium. A stadium designed to hit things. 7,000 tons sounds modest until you remember it is squeezing a piece of glowing steel the size of a filing cabinet. The press sits inside a hall the size of an aircraft hangar, next to a lake because forging drinks water and electricity in serious quantities. The control room is quiet. The machine is not. The operator watches the ram descend and speaks softly into a headset, as if not to startle it. has to stay in a narrow window the whole time, overheat, and the grain grows coarse enough to weaken the part. Undercook, and the steel resists, cracks show up, and someone gets a very unpleasant meeting invitation. The operator reads the color of the metal the same way a cook reads a griddle, only the griddle weighs 12 tons and lights up half the shop. Every squeeze trims height, spreads width, and packs the interior tighter. That interior work is the real product. Not every forging press works alone. Some are stitched into a lime, where bars feed in cold, get induction heated in seconds, get sheared, and hit the press already glowing. A conveyor becomes a moving cafeteria for hungry machinery. Output stacks up as identical shell casings before the first coffee break is over. Presses squeeze slowly. Hammers work the other way, fast, loud, and set to a beat you can hear from the parking lot. A modern CNC hydraulic hammer can land 90 blows a minute, and every blow is metered by the controller. It decides how hard the ram falls, how many strikes, and when the die opens so the next billet drops in. Precision at that speed is what turns raw slugs into wrenches, pliers, scissors, and small automotive parts. You have almost certainly held something in the last week that started life getting punched into shape by a machine bigger than your kitchen. The die does the sculpting, the hammer only supplies energy. Flash, the thin ring squeezed out around the edge, gets sheared off downstream and melted back into the next heat. Nothing on the floor gets wasted, except operator sleep. Which raises the next question: how does the shape itself get decided? And that is where forging stops being one thing. Open die means nothing is enclosing the workpiece. It sits between two shaped tools, and the press works it a section at a time, the way you would flatten dough with a very serious rolling pin, if your rolling pin weighed 40 tons. The upside is scale. Open die can handle forgings over 150 tons, which is bigger than any closed die ever built. Shafts, blocks, ring blanks, pressure vessel sections all start this way. The downside is that nothing is telling the metal where to go, so the operator has to know exactly where to send it. Between strokes, manipulators rotate the workpiece and shift it lengthwise, so the press works one zone at a time. It looks slow because it is slow, but a shortcut here shows up later as a cracked shaft in service, and that is not a rework, it is an investigation. Careful beats quick. Open die forging has its own vocabulary, and it is worth knowing a few words. Upsetting is the first move. The billet stands on its end, the press pushes down, and the workpiece gets shorter and wider. That squashes internal voids and starts aligning the grain. Then comes drawing out, where the workpiece is turned on its side and squeezed along its length to make it longer and thinner. Step forging combines the two, working the metal into stages of different diameters along one shaft. Progressive forging into round takes a squarish billet and, blow by blow, turns it into a clean cylinder, sometimes on the same press, sometimes on a hammer. You could describe this as sculpture if sculptures worked with something the temperature of lava and the weight of a truck. The point of all these moves is not aesthetic. Every rotation and every squeeze is placing the grain flow of the finished part where the loads will hit hardest. Closed die is the other half of the coin. The heated blank drops into a cavity that already has the finished shape carved into it. The press comes down, the metal flows into every corner, excess squeezes out as flash. One stroke, sometimes two, and the part is done. Same shape every time, which is the whole point. Then straight into the water for a quenching hiss loud enough to make a first-time visitor jump. When two tools cannot keep the metal in line, you add two more. A 4-die machine grips the workpiece from top, bottom, and both sides at once, squeezing from every direction. That sounds like overkill until you see what 2 dies do to a long bar. Squeeze from above and below, and metal escapes sideways, so the cross-section wanders. 4 dies close every exit. The workpiece has nowhere to go, so it gets denser instead of longer in the wrong places. The result is a shaft with consistent cross-section end to end, which is exactly what the next CNC lathe wants. Compressive stress from every side also tightens grain flow far beyond what 2 dies can reach. Alloy steel is a picky material. It carries chromium, molybdenum, nickel, sometimes vanadium, elements that give the finished part its strength and toughness. Those same elements make the steel harder to move under the press. It resists deformation more than plain carbon steel, so the forging temperature window is narrower, and the required force is higher. This is why the pump room next door looks like the engine bay of a ship. Rows of hydraulic pumps push oil at pressures that would slice a finger off into cylinders large enough to sit inside. The gauges twitch every time the ram comes down. Somewhere in another building, an electricity meter is having a bad afternoon. Not all forging is giant and slow. Some of it is small, hot, and built for continuous production. A steel ball line looks more like a sport than a factory. A robot grabs a bright orange steel slug from the heater and drops it into a CNC hammer, shaping it into a rough ball in a single blow. The ball then rolls onto a skew rolling mill, where 2 angled rollers with helical grooves spin and round it into a sphere within seconds. The process works much like rolling dough by hand, but at temperatures no glove could withstand. Production runs continuously, measured in balls per minute, 24 hours a day, while operators mainly monitor the system. Automated, cleaner, and remarkably compact. A flange looks simple. It is not. Every flange starts as a round billet, gets sawed to length, heated to bright orange, and dropped into a closed die. The press flows the metal into the ring shape. Then the piece goes straight into the quench pool, where steam boils off like the flange is angry about being cooled. After that, everything you see is subtraction, turning, drilling, boring, until only the finished flange remains. Grain flow inside the ring is the reason forged flanges outlast cast ones in pressure service. That is not marketing, that is metallurgy. A forged pipe is not welded from a rolled sheet, it is punched. A hot billet gets pierced through the middle to create the hollow, then the outside is worked down to size on the forging hammer. The pipe grows longer with every strike, like squeezing toothpaste from a very tired tube. If the toothpaste weighed 3 tons and glowed. The wall stays uniform because forging closes voids the whole way through. On a fully automated closed die line, humans do surprisingly little of the actual forging. Robot arms pull glowing billets from induction heaters, drop them into the press, and pull the finished shape out before the die reopens. Cycle times run in seconds. Nobody stands closer than they have to, because closer than they have to is code for wanting to test their life insurance. The workers you see are watching screens, not swinging tongs. And then there are the rings that make everything else look reasonable. A seamless austenitic stainless steel ring, 15.673 meters across, big enough to park an airliner inside. The record holder gets swung by crane over a quench pool the size of a swimming pool. And the moment it hits the water, the entire building fills with steam. That is the loudest hiss you will ever hear from an object that is not alive. A ring that diameter is not decoration. It goes into things like large offshore structures and heavy wind hardware. Which is a fine segue, because rings are where forging gets really interesting. Some of the strongest parts in industry are not solid blocks, they are rings. A seamless rolled ring starts life as a round billet. It gets upset flat on a 30 meganewton press, then punched through the middle to make a donut. That donut is where the interesting move begins. The blank is reheated, then loaded onto a ring rolling mill. Two rollers, one on the outside, one on the inside, squeeze the wall of the donut and gradually reduce its thickness. As the wall gets thinner, the ring diameter grows. Two axial rollers control the height at the same time. The finished ring keeps its grain flowing all the way around the circumference. That is the whole reason to do it this way.
I don't think I can take this anymore. I might just break.
Ring rolling scales in ways that get out of hand quickly. Diameters run from 200 millimeters up to 9.5 meters. Weights climb to 30 tons. Height up to 1.6 meters, width up to 1 meter. You could walk through the finished part without ducking, and that is before the ring gets machined into a wind tower flange, a slew drive inner ring, or a bearing outer race. Multi-point temperature sensors watch the furnace so the billet heats evenly. CAD software plans the forging ratio in advance because guessing costs money. Every step is recorded because at this size, we think it is fine is not an acceptable answer. Now, put a train on top of a wheel and multiply by 200 cars. A railroad wheel carries 15 to 20 tons of load, at speed, over rail joints, for years, with the only rest coming when a bearing seizes and the maintenance crew swears at somebody. The wheel plant at Bela uses bottom pressure pouring of molten metal into graphite molds, one wheel every 2 to 3 minutes at peak. That is the cast route. The forged route, which we will come back to, is used where the load is even nastier. Either way, the finished wheel has to resist 3 things at once: contact fatigue where it meets the rail, wear on the tread, and cracks starting from small flaws. Get any one of those wrong, and you find out about it during a derailment, which is a very expensive way to learn. The plant runs multiple types now: coach, wagon, container wagon, from a facility that 10 years ago was making 1/3 of its capacity. Forged train wheels follow a different route. A hot blank enters a closed forging die and is shaped in a single blow, then rolls to a mill that finishes the rim profile to precise dimensions. Between cycles, the dies are sprayed with lubricant to keep hot steel from sticking and bringing production to a halt. Laser sensors check wheel diameter at every stage, because the tolerance for a wheel running at 300 kilometers per hour leaves almost no room for error. Finished wheels stack in warm rows, waiting for machining and heat treatment. They will carry high-speed trains, where a wheel failure is more than a maintenance problem. It becomes a headline. Bearing rings are the quiet workhorses of forging. Nobody notices them until one fails, at which point the machine they were inside becomes a paperweight. A bearing ring has to be dimensionally perfect. Ovality of a fraction of a millimeter means the balls or rollers ride unevenly, load concentrates on one spot, and the ring pits itself to death. Forged rolled rings solve this because ring rolling creates a continuous grain flow around the circumference. There is no seam, no weld, no starting point of weakness. Whatever direction the load comes from, the material has grain going the right way to handle it. The finished rings then get turned, ground, and inspected on CMMs that measure to a few microns. What you see leaving the factory looks like polished sculpture. What matters is invisible, sitting inside the crystal structure. A slewing bearing is a ring that carries an entire piece of equipment on top of it. Cranes, wind turbines, excavator bodies, all of them rotate on one of these. When one comes apart for service, the size becomes obvious. Off-highway wheels live a rougher life than anything on a road. A haul truck wheel in a mine goes under 100 tons of rock over broken ground. If the wheel cracks, the tire follows, and neither is cheap to replace. Rims are stamped from thick plate, welded, and stress-relieved before they ever see a paint booth. The bigger ones get forged sections where the load is worst because forged metal handles impact that welded plate simply cannot. Forged wheels can be machined thinner and lighter than anything cast or cut from a plate. Why? Grain flow. A forged blank has metal fibers running in the direction of the eventual spokes, so material can be removed aggressively without weakening the wheel. A 5-axis mill hollows out spoke faces, undercuts hub sections, and leaves a wheel that looks like it has been on a diet, because it has. The remaining metal is exactly where the loads are. Bearings range from a 6mm bore up to 2 meters across. The tiny ones spin inside dental drills. The large ones sit under industrial machinery weighing hundreds of tons. Same principle, 30,000 times the load. Precision testing on every ring is not optional. A bearing that leaves the factory 20 microns out will destroy itself within weeks. Bearing production is forging and grinding, in that order, for a very long time. Rods get forged into rough rings. Rings get turned, heat-treated in salt baths, quenched, then ground to final size. The grinding sparks look aggressive, but they are removing microns at a time. After that, roller cages get pressed from sheet, rollers are cut and tumbled, and the whole thing gets assembled by hand. Now the rings roll aside for the shafts. Every forged shaft starts life as a clean, round bar, and clean means clean. An electric arc furnace melts scrap into a very picky liquid, refines it in the ladle, degasses it, and pours it into continuous casting molds that produce billets, blooms, or rounds. The cleaner the steel, the fewer places a fatigue crack has to start 20 years later. That matters enormously for shaft. Now watch what happens after forging. A shaft comes off the press oversized on purpose. The forging is meant to establish grain flow, not final dimensions. Everything after that is subtraction. A 32-ton horizontal lathe grips one end of a shaft the length of a small truck and spins it slowly, while a carbide tool peels off ribbons of steel in coolant spray. Swing over the bed reaches 2 meters, meaning workpieces up to 2 meters in diameter fit under the tool. The chips coming off look almost decorative until you realize each one is hot enough to burn skin through denim. The operator stands on a platform beside the machine and watches the readouts more than the workpiece. Modern heavy lathes are numerically controlled, so the human's job is monitoring, correcting, and stopping the machine if something sounds wrong. You cannot unmachine a shaft. Every mistake is expensive. A 120-ton face lathe handles the shafts that heavy machinery cannot run without. Turbine rotor shafts, generator shafts, mill drive shafts. All of them meet a machine like this. The workpiece rides horizontally between 2 massive centers while the cutting carriage travels along its length. Because the shaft can weigh more than a delivery truck, every part of the lathe is overbuilt. The bed, the drive, the tailstock. Chatter is what everyone here is trying to avoid. Even light vibration leaves marks on the surface, and marks on a shaft spinning thousands of RPM are how bearings start failing early. A truck axle is not one piece of metal. It is more than 20 operations and a lot of patience. The axle beam starts as a tube. It gets hot rolled to the target wall thickness, both ends get cut square, then a machine pushes each end into a square cross-section. That is where the wheel spindle later attaches. Heat treatment goes next, in a furnace long enough to hold several beams end to end, followed by shot blasting to clean the surface. Then straightening, because heat treatment always warps things a little. Nobody has yet built a heat treatment process that produces perfectly straight parts, and if they had, they would be very rich. After that comes fine machining of the spindle diameters, drilling of oil holes, medium-frequency induction quenching of the wear surfaces, and outer circle grinding to hit final tolerance. Brake brackets get welded on, bearings get pressed in, and the axle assembly line delivers finished units at one every few minutes. Forging is not one temperature, it is 3. Hot forging works at bright orange, warm forging at dull red, cold forging at room temperature. Each earns its place. Hot handles large shapes and heavy deformation. Warm gives tighter tolerances, so parts come off closer to final size and skip machining steps. Cold pushes the metal without any heat at all, which gives excellent surface finish and dimensional accuracy. The price is much higher press forces. Modern drivetrain plants use all 3, sometimes on the same production line. A differential gear might be warm-forged near net, then cold-sized to final tolerance, then induction-hardened only on the tooth surfaces. The teeth become wear-resistant while the core stays tough. 2 properties in one part, achieved by heating only the outside. A crankshaft is where forging stops being abstract and starts being personal. Every combustion event, every piston stroke, every revolution of the engine, the crankshaft absorbs the load and converts it into rotation. A road trip engine spinning a few thousand RPM racks up millions of cycles before you have finished lunch. Millions! That is why cast crankshafts are fine for mild duty and forged ones own everything demanding. Heavy trucks, marine engines, industrial diesels, high-performance motors. The starting billet is heated, then squeezed through multiple die stations that gradually build the offset throws and counterweights. Grain flow wraps around every throw, following the exact geometry of the finished part. That is the difference between a shaft that lasts 1,000,000 kilometers and one that cracks somewhere around 200,000. After forging comes a long list of operations: turning, drilling oil passages, grinding journals to microns, induction hardening the wear surfaces, and balancing. Skip the balancing check and the engine will happily walk itself across the shop floor. Complete crankshaft machining on one horizontal turn mill center is a relatively recent luxury. For decades, a crankshaft went from station to station, turning here, milling there, drilling somewhere else, grinding in a different building. Every setup added time, and every setup added error. Modern turn mill centers do most of it in one clamping. Roughing removes the excess forging stock in loud sparking cuts. Finishing follows, with coolant spraying and the workpiece rotating between polymer concrete supports engineered to dampen vibration. Linear roller guideways keep the tool position stable over years of production. The result? A crankshaft that comes off the machine ready for grinding and heat treatment, with journals accurate to microns, and the throws exactly where the design says they should be. For high-volume automotive production, this is what makes a modern engine possible at a price anyone can afford. The pin journals and main journals emerge from the machine already close to bearing tolerance. Then there are the crankshafts nobody replaces because nobody wants the bill. This one is 37 feet long, weighs over 37,000 pounds, and came out of a 12,000 horsepower pipeline compressor. A new one takes months to build and costs more than a house, so it gets repaired. Chrome plating rebuilds the worn journal surfaces. Grinding brings them back to spec. A row of wheels works several throws at once, coolant spraying. Then the shaft goes back to work for another decade, and the reason it can is what happens next. Forging gives you the shape and the grain flow. Heat treatment gives you the actual strength. Skip the second one, and the first one was a very expensive waste of time. A leaf spring on a rail vehicle is a good place to start because the load on it is relentless. Every wheel bump, every rail joint, every day for decades. The finished spring goes into a shot peening machine where thousands of small steel pellets get fired at the surface by high-speed turbines. Each pellet dents the surface a tiny amount. That is the whole point. A shot peen surface is compressed, and compressed metal has a very hard time cracking. Fatigue cracks always start at the surface, so putting the surface into compression is the cheapest way to make a spring last 2 or 3 times longer. The machines look loud because they are loud. The blast media is filtered, recycled, and fired again thousands of times per minute every minute the plant is running. A gear tooth has 2 conflicting requirements. The surface has to be hard so it does not wear out from meshing with the next gear. The core has to be tough so it does not snap when the load spikes. You cannot get both from the same heat treatment applied to the whole part. So induction scanners heat only the teeth to bright red, then quench them immediately in liquid. Hard skin, tough heart. Every tooth gets the same treatment, which sounds obvious until you try to do it any other way. Bearing rings and slew rings have a specific problem. Where the induction coil starts and where it ends, the metal cools differently, leaving a soft spot. On a wind turbine slew ring, that soft zone is where failure begins 20 years later. A patented scanning method now runs seamlessly around the whole ring. No start, no end, no weak segment. The scanner does not stop, so the metallurgy does not either. After the press comes the furnace. And after the furnace comes another furnace. Hardening at up to 950 degrees Celsius. Tempering at up to 750 degrees Celsius. Solution annealing at 1250 degrees Celsius. 33 furnaces working in shifts, moving forgings through a controlled thermal cycle that draws the actual mechanical properties out of the steel. A cold forging looks finished, but is metallurgically half done. The right heat treatment turns it into a part that resists wear, machines cleanly, and holds up in cold weather without going brittle. A ball screw is a shaft with a helical groove that carries recirculating steel balls, and it has to be hard in exactly the right places. Diameters run from 9 mm up to 65 mm, lengths up to 6.2 meters. The induction coil scans along the shaft at 15 to 35 mm per second, while a 150 kilowatts medium-frequency generator drives the heating. The groove surface reaches hardening temperature in seconds, then a spray quench locks it in. The core stays soft enough to absorb shock. The surface gets hard enough to survive millions of ball passes. The whole thing is CNC controlled because doing this by hand is how expensive things get scrapped. For gears where warpage would ruin the part, the whole part cannot go in the furnace. A laser hardening head mounted on a robot arm walks along the toothed flanks and heats a strip a few millimeters wide to red hot. Self-quenching happens through the surrounding cold metal. No water bath, no distortion. Only the wear surface gets hardened, and only the part of the wear surface that needs it. Now watch what quenching actually does. A stainless steel piece heated to 1950 degrees Fahrenheit drops into a tub of water. The moment it hits, steam blasts upward and the surface starts boiling like a special effects shot. Inside the steel, something more interesting happens. At high temperature, the crystal structure is one arrangement, soft, ductile, spacious. Cool it slowly, and the atoms rearrange back into their comfortable state. Cool it fast enough with a quench, and they cannot. They freeze in a distorted, hard crystal called martensite. That is where the hardness comes from, trapped physics, not chemistry. The trade-off is brittleness, so the part goes back into a lower temperature furnace for tempering, which softens it just enough to survive the first real bump. Get the timing wrong and everything you saw upstream turns into an expensive doorstop. All of this, the presses, hammers, rolling, the heat treatment, is only worth doing because of where the parts end up. Hot forging is used when the shape has to change a lot. A steel bar enters glowing bright orange, goes through electrical upsetting, then a friction screw press flattens and forms it. The metal moves the way the die tells it to, because the metal has no better options at that temperature. Automotive, agricultural, construction, that is where these end up. Cold forging is the quiet sibling, and in some ways the more clever one. No furnace, no glowing metal, no clouds of steam. The wire feedstock enters at room temperature and gets pushed through a multi-stage press where punches shape it in successive cavities. Each station changes the geometry a little more until a plain wire has become a hollow fastener or a complex automotive part. Because the steel is cold, it work hardens as it deforms. The finished part is actually stronger than the wire it started from. Surface finish is excellent because no scale forms. Dimensional accuracy is high because there is no thermal expansion to worry about. The trade-off is press force. Cold steel resists, and the tooling has to be very good and very well made, or it does not last a shift. Steering tie rods and engine push rods are two places you very much want cold forging. Both parts see millions of load cycles. Both have to hold precise dimensions. Both are safety critical. A tie rod that fails on a highway is not a warranty claim. It is a much worse phone call. Automated inspection checks every piece before it leaves the line. Then there are the parts nobody makes cold. Some shapes demand the biggest hammer in the building. A cylindrical billet the color of sunset gets positioned under a blue hydraulic press the height of a two-story house. The ram comes down, the workpiece elongates, the operator rotates it a few degrees, and the ram comes down again. In under a minute, a solid billet becomes a hollow cylinder that no other process could produce in one piece. The finished shape carries grain flow along its full length. Forged cylinders are what you get when a hydraulic pump has to survive 20 years of pressure spikes. A glowing billet gets shaped between the jaws of a mandrel forging machine, which compresses the outside while a mandrel forms the inside. The cylinder walls end up uniform, dense, and free of the internal voids that cast cylinders inherit. Then a forklift moves the still red-hot part to the machining shop, where a large lathe honing tool works the inside surface with coolant spraying everywhere. The interior finish has to be good enough that a hydraulic seal can ride on it for millions of strokes without leaking. Every part of this, forging, cooling, machining, honing, is aimed at one thing: keeping high-pressure fluid inside the cylinder where it belongs, not on the shop floor. And finally, the payoff that ties everything together: turbine blade steel. A steam turbine blade lives inside a machine spinning at thousands of RPM in 1200 degrees Fahrenheit steam under centrifugal loads that would tear ordinary steel apart. The alloy, a hardenable stainless grade, is melted in an electric arc furnace, refined in the ladle, vacuum degassed, then remelted through electroslag refining to clean the ingot. That clean ingot gets forged into billets under a heavy press, the same way every serious shaft in this video began. What makes it work is not any one step, it is the stack. Grain flow from forging, cleanliness from refining, hardness from heat treatment, geometry from machining. 4 properties compounded into one part. That is what forged means when the label is real. Cut a corner anywhere along that stack and the blade fails at operating temperature, the second worst place to find out. Everything before this moment was preparation. Now the parts go to work. Every part in this video ends up somewhere real. Right now, forged crankshafts are running inside container ship engines crossing the Pacific. Forged wheels are carrying passengers on high-speed rail lines through Europe. Forged bearing rings are turning under wind turbines in the North Sea. Forged cylinders are holding pressure on hydraulic presses that are, at this very moment, forging the next generation of parts. The chain never breaks. So here's a question a lot of people are arguing about right now. As electric vehicles replace combustion engines, and as more parts get 3D printed instead of forged, does forging still have a future for the next 50 years, or is it slowly getting phased out of the heavy industries that built it? Drop your answer in the comments. We read every one. Thanks for staying to the end. If this took you somewhere new, hit subscribe, and we will see you on the next build.